All right, good evening, everyone, and welcome back for your second class. I'm impressed with how many of you are still here in person. I'm glad it makes it seem worthwhile coming in and giving the lecture in person. Welcome back for your second class. I'm impressed with how many. It's working. Great. So that means I've posted a couple links to our YouTube channel. If you want to catch any of this a second time or review it later, it will be there for you to watch. So in today's session, we're going to continue sort of along the same lines as we did yesterday. I'm going to start out with a fairly lengthy review of session number 1, just to help ease everyone into the semester. I'll always do some review of the previous class, but today will be a little longer than usual. I want to make sure to have a non-traumatic start to the semester for those of you who have been out of math and statistics classes for a while. So we'll go again over the data types and continue with some of the initial discussion we had about certain kinds of visualizations for these data types: frequency tables, bar plots, histograms, box plots. But I'll go into a little bit more detail in those today, and then I'll discuss some numerical summaries of data, like mean, median, mode, standard deviation, variance. So I know now from all of your introductions that we have at least one person here with a minor in statistics. So I apologize to that person, but we'll move on to other things soon. But we're starting from the basics here for everyone. So to review some of the vocabulary that we introduced last time, and feel free to pipe up if there was something else new that I didn't include in the review here. But the population refers to the entire group of interest. So there are two parts of that. One is that it is entire, and the other one is that it is the group of interest. So that could mean everyone in the world. It could mean adults in New York. It could mean any number of things, but it's the entire group that we're intending to study. And a sample is some subset of that population that we actually observe. I refer to records or observations as the data for one individual. And these two of the three parts of this statistics that I introduced were descriptive statistics, referring to summarization and visualization, which is everything that we're doing in these first two classes, and inferential statistics, which is inferring something about the population from our sample. A variable is any characteristic that is recorded for the subjects in a study, and we covered these three types of variables: the two nominal types, binary and categorical. Binary, things like, well, treatment group, if it is just treatment and control, that's a binary variable. Marital status could be binary or categorical, and race could be binary, categorical, depending on how it is being coded. Ordinal data were the first type that were not nominal. So the nominal variable types were nominally numbers if we recode them as numbers, but they're not really numbers. The rules of arithmetic do not apply. And ordinal numbers are again not really numbers, but they have an order, unlike nominal data. So birth order among siblings, or other kinds of ranking first, second, and third. And I thought I would note that sometimes nominal and ordinal variables can be lumped together. They're both categorical data types. So if you hear categorical data, that could refer to both nominal and ordinal data types. And then quantitative data are really numbers. So these are numbers in the classical sense, in that the rules of arithmetic apply. You can add, subtract, multiply, and divide them. And this distinction between different quantitative variables is a little bit can be a little bit hard to make sometimes, but discrete data are ones where not all values are possible between the boundaries. Only certain discrete values, such as integers, are allowable, whereas a continuous variable, so number of children, would be a classic discrete variable because it tends not to be so large that that you can ignore the discreteness. It is numeric, but only integer values are allowed, and it's not so large. Whereas in those examples we did of like the number of deaths due to cancer and heart disease, that's also a count, it's also discrete, but it doesn't matter that much because we're talking about hundreds of thousands of people, and that distinction is not so important. Height, weight, and age are classic examples of quantitative variables where every value between the possible limits can occur. Even though you can correctly point out that the measurements that we use to collect these tend to take only discrete measurements. So when you take a ruler, you mark your height on the wall and measure with a ruler, that ruler is only going to go down to 1/16 of an inch or millimeters. So you still have discrete limits to how you can measure quantitative variables. But at least in theory, these are, you can have any height, weight, or age between 0 and the maximum possible value. So for nominal and ordinal data, that is categorical data, you can summarize these as so-called frequency tables or contingency tables, which is just a fancy way of saying a list of how many of each possible value occur. So in that example of a clinical trial for a pain reliever, these are the one-dimensional frequency tables. There are 50 treatments, 50 controls, and overall 20 people reporting mild pain, 30 reporting moderate, 50 reporting severe. So this is a so-called one-by-one frequency table or contingency table. And those can also be visualized as bar plots, which display the same information as a one-by-one frequency table. I'm just calling it 1 by because it's only has one variable in it here. Pie charts are another alternative, but one that tend to be frowned on by statisticians who don't know how to have fun. Those who know how to have fun know that pie charts have their place sometimes. That's why they can be popular in newspapers and stuff, because they can be visually appealing, like this example of a pie, part of which has been eaten and part of which has not been eaten. Can you tell which is which? You're a tough crowd. Has most of the pie been eaten or not? No, most of the pie has not been eaten. That's kind of the level of quantitativeness of a pie chart. Most of it has been eaten. It's pretty hard to say, is this, I don't know, 60% or 70%, but you can tell it's mostly been eaten. Or sorry, mostly not been eaten. Another reason statisticians frown on pie charts is that anything that you can put in a pie chart, you can also put in a bar chart, and it will be more quantitative, such as this bar chart showing the amount eaten and not eaten, which is not nearly as much fun, but you can at least read directly off here that this is something very close to 65% not eaten. But this is a case where I would stick to the pie chart. So we use these frequencies and proportions in frequency tables and bar plots to summarize nominal or ordinal data. So if, for example, 4 students out of 40 received an A, then the frequency is 4. That's just the count. The proportion, or the relative frequency, is 10%, 4 out of 40. Or sorry, the proportion is 0.1, and the percentage is 10%. So these are all of our tools for numeric summaries of a single categorical variable. And any of these can be used either in a frequency table or a bar plot or a pie chart. Of the options that you have, now we're going to quantitative variables. The three that I showed you last class, the dot plot, the histogram, and the box plot, can kind of be summarized like this, that at the top, this is the most detail and the least summarization. The dot plot, that's because this shows every single observation, whereas towards the bottom, we get more summarization and less detail. And I say that the box plot, in some ways, it has details that the histogram does not have. However, the histogram shows you fairly detailed, depending on your bin width, about the entire distribution, whereas the box plot shows you major parts of the distribution, those quartiles. But these are helpful for identifying key features of a quantitative variable, such as their central tendency, where most of the data are, the spread, how spread out it is, and the shape of that spread, such as skew and outliers. Again, these dot plots, the example I showed last time was just little like dashes along a single axis. This is another way it's done sometimes, where you actually stack up the dots, so it becomes almost like a histogram. This is something you could do with a discrete variable, or if you did some grouping together or binning of a continuous variable. Histograms are far more widely used, though, and this is essentially creating bins and counting the number of observations in each of those bins, and then making a bar chart. That newly binned data becomes an ordinal variable because there are discrete bins with counts in each of them. So the kind of data that you would put in a frequency table or a bar plot, and then it is displayed as a bar plot with these bins just in order. You should keep in mind when you make histograms that the one that you get by default from your software is not the only histogram you could make for a variable. There's some default setting there for the width of these bins, and that can have quite an effect on the appearance of your histogram. So on the left here, this set of weights is divided into 10-pound bins, and so you see a lot of detail. And then in 20-pound bins, you see somewhat less detail, but you get a little bit better idea of this kind of bell shape. And at 30 pounds, there's even less detail, but it is in some ways easier to see this skewed shape. It's sort of skewed towards the right. But it looks pretty, these are exactly the same data, and they look kind of different in these three histograms. So it's worth keeping in mind that the histogram isn't the entire story of a quantitative variable, and you can miss things or get lost in details depending on that bin size. The main things that you will look for in a histogram are the center, the spread, and the shape. The center just being the highest point, generally, in the histogram. While there are a couple of kinds of centers, that highest point would be the mode for that particular bin size. But if you can spot the place where half the data points are above and half are below, that would be the median. It's a little bit hard to assess the median in a histogram. You can kind of guess. It looks like it's, in this one, it looks like it's about, I don't know, one. It's a little hard to read the labels here. I think that 250, 150, so that's 200. So it looks like it's somewhere around 175. And this one, yeah, probably around 175. Although here you would maybe put it a little bit lower, even though that median is exactly the same. There's only one median. But it's an approximate estimate of it. Actually, one thing that's kind of worth putting out here, if you look at this one with the 20-pound bins, it almost looks like a bimodal distribution, like there are two different peaks in here. But the fact that, you know, in the 10-pound ones, this just looks like a blip and you don't see it at all with the larger one. It's hard to say, but if I had to guess, I would say that might just be sampling variation, because these are not very many observations. This is only a count of 4 here. So, you know, if these were counts of hundreds, then maybe this would be a real pattern. Instead, this is quite likely just sampling variation associated with our sample. I'll talk more about sampling variation as the semester goes on. So there's the center, the spread, how, you know, what that range and the shape of it within that range, and whether it is symmetric, skewed left, or skewed right. So symmetric distribution looks like a mirror image. You can put a line in the middle and it looks approximately the same on either side of that line. A left skew means that the data spread out more to the left than to the right, and a right skew is the opposite, that it skews out more to the right. Skewness is pretty common in certain types of data. A couple classic examples are lifespan tends to be left skewed because most people live to be, at least in the US, live to be adults, and so this would be something like 70 years with some spread. You don't live to be too much older than that, but there are occasional deaths of youths due to accidents or other things, and so you have this long tail going out to the left. There's few people dying at very young ages, and the large majority who survive to this typical life expectancy, and then not too much beyond that. Whereas incomes are a classic example of a right skewed distribution, where you have lots of incomes at this sort of middle level. It doesn't go too far to the left of that because you run into 0, but there's no upper limit, at least in a capitalist economy. You have people who can earn, there's no upper limit on the amount. So you have this very long tail where a few people earn a lot of money. I alluded to this before, but modality is something that can be identified in a histogram. You have to be a little bit careful assessing this by eye, but here's a fairly clear example of a variable with 1 mode and a variable with 2 modes, a bimodal variable. There are statistical tests for assessing bimodality, and if you were unclear about it, you would want to use one of those to tell whether you're reading too much into your sample or not. But something like this is very clear. So these are higher counts. And the one I showed you before, the maximums were like 4 or 5 counts. Here they're like 20. So this drop from a count of 22 down to 1 or 2, that doesn't happen by chance. So this is a pretty clearly bimodal distribution. There's lots of counts in both modes and very clear separation between them. And an outlier is something that does not have a very clear definition. There are lots of different ideas about what constitutes an outlier and different definitions. But in general, it's just an observation that falls far from the rest of the data. That's the most general way that I could state it. I can mention that sometimes outliers are actually expected. There are some certain distributions, and I'll show you some examples, just have outliers. They're part of the random distribution, whereas other observations or other outliers are not part of the same distribution, and they occur because of something different than the rest of the data. So this is an example that looks like we have lots of observations that are from a nice normal distribution, and then this one way out here that looks like it is not from this same normal distribution. And as such, they deserve some special attention and consideration about whether or not it is justifiable to remove them. If you're not sure, you should be hesitant to remove any data because it may be telling you something. It may be a part of your population that you've been just lucky to observe. But it could be in this case that it was just a recording error, that someone forgot to put in a decimal place or something like that. So it normally would require some kind of additional investigation to try to determine whether this is a plausible outlier or not. We discussed this plot last time. I'll just go through it once more because box plots are amazing. They show quantitatively many of the same properties that you get from a histogram, but summarize it in this single box where the thick line in the middle is the median, which is also the second quartile. The outer boxes are the first and third quartiles. And this difference, this width of the box, is called the interquartile range, or IQR. And then these whiskers extend out from the median plus 1.5 times this IQR to minus 1.5 times this IQR, with the exception that if there are no data points out this far, it only goes as far as your furthest data point. So it's the maximum length of this whisker is 1.5 times the IQR, so 1.5 times the width of this box. And anything that you see outside that might be considered an outlier. It doesn't mean it is an outlier. It doesn't mean there's anything unexpected about it. It just means that it's it's far from typical from the center of this distribution. As you'll see in certain distributions, even when there's nothing wrong, there's no measurement error, no recording error, you still can get plenty of points outside of these whiskers, just because it's part of the distribution. One very nice thing about the box plot is that you can compare multiple distributions. This gets kind of hard with a histogram because you have to plot them over each other. It can be done, that there's plotting functions in R to use like opaqueness to put histograms over one another. I don't think you can do that in SPSS, but you can make box plots, and honestly, they're easier to read for comparing distributions than histograms anyways. So in this example, I'm comparing the distribution of heights in inches between males and females, and it just gives you a very easy visualization of there being a higher median height among the male group and there being a certain amount of overlap, but the minimum is lower among the females, and the maximum actually is almost the same between the two groups. But generally, the central part of the distribution is shifted over. So even if we had 5 different groups here, it's still very easy to compare these distributions using a box plot. That would be almost impossible if you had 5 variables to look at all in one histogram, but it's easy to do with a box plot. Any questions, comments so far before I'll move on to, so this is now our new stuff for this class. Okay, so those were a number of visualizations, which are a great way to get your first introduction to data that you're going to be analyzed. These measures are sort of a good next measure, and they're also often reported in tables in a paper to give a more compact summary of your data. So starting with the mean, this is maybe the oldest statistical concept that we know of in recorded history, and also still one of the most useful. I'm really impressed with how frequently the simple mean is a very useful measure. And all it is the sum of your observations of a quantitative variable divided by the number of observations. That is for a population. I'll show you. There are, no, sorry, I'm getting ahead of myself. Just divided by n, the number of observations. For example, you add up how much each person paid for lunch, so your total bill divided by the number of people, that's your average. If you're going to split it equal ways, you're actually calculating a mean. So this thing we use in statistics, you can also use as an easy way to decide how much each person pays for lunch. This is called capital sigma notation, and it just means a sum. So I'm indicating our variable here, our measurements, with the subscript I, and saying I'm going to sum all of these measurements from the first to the last. So there are n measurements here, and then divide by n to get this value x bar, which is a mean estimated from a sample. So remember I said I would use Greek letters for things about the population. This is, because I'm writing it with a Roman letter and a bar, this is a property of a sample. You should know about the mean that it is not resistant. That is, that it is strongly influenced by outlying values. So in this example, I'm showing several distributions and making a box plot to compare these 4 distributions. So this first one is a normal distribution. You can see the individual data points here, the interquartile range, the whiskers, and you see there's only one here on the bottom that comes outside of the whiskers. It's not a real outlier because this is simulated data, it's truly normal. And I put in red here the mean. So you can see that in this normal distribution, it's symmetric. The mean and the median are essentially the same, right on top of each other. The second distribution is called a log normal distribution. And that means that if you take the logarithm of these values, you'll get a normal distribution. Or if you take a normal distribution and exponentiate it, you get a log normal distribution. So this is an extremely skewed distribution. You can probably, if you think back to your math classes, you know that the exponential function is a rapidly increasing function. So if you have differences in your original scale become products once they're exponentiated. So adding one to your original variable multiplies by something on the exponential scale. So these things that were almost outliers on the normal scale, they're up here, end up way, way up here, looking like strong outliers in the log normal distribution. And here you can see that this red, the mean, is nowhere close to the median anymore. It's up at about the third quartile, the top of the box. The exponential distribution, that's it's the exponential of a uniform distribution. So if you start with uniformly distributed data, take the exponential, you get an exponential distribution. So it's starting with a uniform distribution instead of a normal distribution. It's not nearly as extreme, but you still see you can still see evidence of skew here, both because of the outlying values above the top whisker and because this mean is shifted away from the median. So anytime you see a difference between the mean and the median, it's evidence either of outliers or skew. Because this mean is influenced by outlying values. Finally, a uniform distribution in the box plot, it looks kind of similar to the normal distribution, except that, that the box is wider. I chose limits between -2 and 2, and you see that the box is pretty wide relative to the further values. That's the only way you could distinguish it from the normal distribution. So this is what's great about the box plot, is that in this one plot, I'm able to discuss in quite a bit of detail these 4 different distributions, and I can see differences in each of them. This would take 4 separate histograms and taking care to use the same scale on each of them if I were going to try to do this using histograms. And it would take quite a bit more space and be a bit more difficult to compare them all against each other. The median, it's just the midpoint. It's easy if there are an odd number of observations. It's just the one in the middle where there are equal numbers of values above and below. If it's even, one way to do it is the median of the, or is the average of the 2 middle observations. I'll just mention it, kind of a point of curiosity, that there are different ways of calculating the median, and you get, for a small number of observations, like if you only have like 4 or 10 observations, you'll see differences between different statistical software. So if you do it in Excel and you do it in SPSS, you actually see slightly different answers. So it's usually not a big difference, but a bit of a difference. In terms of percentiles, median is the 50th percentile. So unlike the mean, it is completely resistant to outliers. So if our observations are 1, 2, 3, 4, 5, the median is 3. We change 5 for 1 billion. The median is still 3. And well, if we get rid of that last one, it shifts a little bit down to 2.5. So it's very resistant. You can't change the median too much with any one data point by removing it or adding an outlier or anything like that. And just by way of example, if we stack up the 7 dwarfs from shortest to tallest, here's the median, the guy in the middle. If we add a super tall basketball player, it's still just the one in the middle. The mode is something that you can only really calculate for categorical variables because it's the value that occurs most often. So when I talk about like a unimodal or a bimodal distribution for a quantitative variable, that's done based on the assumption of us having binned the variable, like to make a histogram. So if we make a histogram by binning this variable into this size, then the mode is right here, whatever this value is. But because quantitative variables don't really have a mode, it'll change depending on your decision for the width of the bins. So it's not inherent to the variable itself. So I mentioned this with those 4 distributions, but I just to write it down here. If you have a skewed distribution, you can infer that from differences in the mean, the median, and the mode. So something right skewed because the mean is affected by that skew the most. You will have a mean that is a fair bit larger than the median, and the median larger than the mode. And similarly, with a left skewed distribution, the median is smaller than the mode, and the mean is even smaller. So even if you weren't able to see the distribution in a box plot or a histogram, which would be the easiest ways to infer skew, if you just saw like the mean and the median, you should be able to tell me in which direction it is skewed, just from, say, the mean and the median. Also, just to get this written down for you, percentiles are the value such that for the pth percentile, p% of the observations fall at or below that value. So, if you were to draw the distribution out as this density plot, at the pth percentile, you have this p percentage and 1 minus p below and 1 minus p% above that percentile. So if it's the 90th percentile, 90% of the observations are below and 10% are above. Quartiles are these special percentiles that split the data into 4 equal components, with 25% of the observations in each quartile. And finally, range is another measure of the spread, and all it is the difference between the maximum observation and the minimum observation. So it's kind of a natural one to describe the data. What are the minimum and maximum values and the difference between them? I should note, though, that the range is strongly affected by outliers, of course. Just a single value can completely change the range. And as such, it's also not a stable measurement with respect to sample size. If you, from the same population, if you take a small sample, it will have a small range. The larger the sample you take, the larger that range will get. So it's an interesting numerical summary, but it's also an unstable one. The most unstable of all of the ones that we've learned. So in this example, with a maximum of 250 and a minimum of 100, the range is 150. All right, variance and standard deviation are a measure of spread that are particularly useful for normal distributions. And they are one of the 2 things that define a normal distribution. Before we get to, I will define a normal distribution later. But just in advance, who knows what are the 2 you only need two numbers to completely specify a normal distribution. What are they?
Guess there's a reason for this class.
What?
I said, I guess there's a reason for this class.
There's a reason for this class.
We saw that video.
What are the two parameters that define a normal distribution?
Think about where the center is and how spread out it is.
One of them's on this page. Standard deviation, yep. Or the variance. You can give either one. The standard deviation squared is the variance. Either one of those is one of the two things you need to specify a normal distribution. And what's the other? The mean. Yep. So the mean and the variance or standard deviation completely defines a normal distribution. So the formula is a little bit more complicated than we had for the mean. I'm again showing the formula for estimating the standard deviation or the variance from a sample. It requires first calculating the mean using the formula we had before, and then for each observation, calculating the squares of the differences from the mean. Then summing those and dividing not by n, but by n minus 1, which is a little bit weird. That gives the standard deviation squared, which is the variance. This is a bit of a curiosity, this dividing by n minus 1. And this is specific to estimating the variance for a sample. If we were doing this for a population, we would just divide by n. If you have a hard time remembering which is which, consider this. When you have an entire population, when you calculate the mean, you have an exact value. There's no uncertainty in that mean. You can calculate both the mean and the standard deviation exactly for a population if you have all of the observations. Now, for a sample, we don't have all the observations, so it's only going to be an estimate. And this x minus x bar, this measure of the variance, is based on a mean that we estimated from the sample. And that mean from the sample, it's not exactly right, and it's put in the place that minimizes this sum of squares. So the true, if we happen to have the true population mean here, this sum of squares would be a little bit larger. So because we are underestimating this sum of squares, you divide by something a little bit smaller, and this turns out to be an unbiased estimate of the variance. Meaning that if we took larger and larger samples, or if we repeated our sampling over and over and recalculated the variance, that average would be exactly the same as the population variance. If you didn't do this dividing by n minus 1, because for every sample, the estimated mean would be in a bit different place that underestimates the variance, we would end up with a systematic underestimate of the variance of the population. So what would you do if you had observations of a sample, but you happened to know the exact population mean, and you wanted to estimate the variance from that sample, but we're not using the mean from that sample? Would you divide by n or n minus 1? So let's suppose we've taken a sample, so I'm going to say heights. I've measured the heights of everyone in this room, and I want to estimate the variance of heights. Heights is a nice normally distributed variable in the population. But when I estimate this sum of squares to get the variance, instead of using the mean height of people in this room, I use the mean height for the population of adult New Yorkers, and assume that you're representative of adult New Yorkers. So I'm not using a mean estimated from the sample. I have an exact mean. So then would I divide by n minus 1 or by n? By n. Right. Because by using that correct population mean, this sum of squares is going to be a little bit larger than if we estimated it from our sample. This only makes a difference for small samples. So for like 30 of you here tonight, you wouldn't even notice if we're dividing by 30 or 29. But if it's a sample of size like 5, it makes a big difference. If you put in 5 numbers in your statistical software and run your descriptives and get a mean and standard deviation, those will both be estimated from the sample. So they will use this formula for the standard deviation. Now, these sum of squares are even more sensitive to outliers than the mean was. Remember, with the mean, we just added up the values and divided by n. So in these 4 distributions, here were the deviations from the true mean. You can see how there's more skew and outliers in the log normal distribution. Well, for the standard deviation, it's the square of these deviations. So if you thought the mean was sensitive to outliers, the standard deviation is much more sensitive to outliers because you square those deviations. So now these outliers in the log normal distribution, they really dominate the estimate of the standard deviation. So standard deviation is useful for distributions that are normal or close to normal, not very useful for something like this log normal distribution because it's so sensitive to these to this long tail that it has. So it is not robust to outliers or skew, but it is convenient and very important for describing normal distributions. Few properties of standard deviation. One, it has the same units as the observed variable. So if we measure heights in inches, then the standard deviation will be in inches. And it measures the spread of the data. It's always positive unless all observations have the same value. So as soon as you have any 2 observations that are different from each other, the standard deviation becomes positive. And of course, as the spread or those deviations from the mean increase, S gets larger. It is not resistant to outliers or skew. To show this nice box plot again, I've added to it so the thick red lines are still the means, but I have added thin red lines at plus or minus 1 standard deviation and dashed lines at plus or minus 2 standard deviations. So this is kind of informative about the box plot when made for a normally distributed variable, in that the IQR, these boxes, are fairly close to the plus or minus 1 standard deviation from the mean, and the whiskers are fairly close to 2 standard deviations from the mean, if it's normally distributed data. it's not normally distributed data, then all bets are off. And remember for the log normal, how I said, whoa, the mean is quite a bit different from the median? Well, the standard deviations now are really changed, and they're no longer anywhere close to the box or the whiskers. So well, the 2 standard deviations below isn't even on the plot, plus 2 standard deviations is way up here. Same thing to a lesser extent with the exponential distribution. And again, the uniform distribution looks sort of similar to the normal distribution in this visualization. So the take-home message here is that mean is not resistant to outliers, but standard deviation is much more sensitive to outliers and skew. And what numerical measure is the most sensitive of them all to outliers? Range, very good. That's great. Yes, the range is the most sensitive of them all to outliers. There are alternative measures of spread. I've mentioned the interquartile range. This is a robust measure in that it is not sensitive at all to outliers. And it is just the 3rd quartile minus the 1st quartile. The mean absolute deviation, or MAD, is the median of the differences between each observation and the median. You do see it come up every now and then. It's another robust measure. Well in the range, we've mentioned that. Not robust. I put stars by these 2 because they are robust to outliers and skew. So if you have data which are obviously extremely skewed, like the income data or age data, one possibility is just to create bins and summarize the amounts in each bin. So say there are this many people who had a lifespan of less than 20 years, this many from 20 to 40, 40 to 60. That's one way to summarize skewed data. And another is with things like this, by providing things like medians and MADs. In probably most public health data that you will report, you'll deal with it by categorizing the data and reporting the amount in certain bins. Here is your vocabulary summary of the day. We covered, again, these dot plots, histograms, and box plots as ways to summarize a quantitative variable, and mean, median, and mode as numerical summaries of a quantitative variable. We have percentiles, quartiles as summaries of the other summaries of the distribution, and standard deviation for describing the spread of a normal distribution, and IQR, median absolute deviation, and range for also measuring spread. We covered the capital sigma notation. This, as well as the notation for samples and populations, again, are summarized in your syllabus. We covered unimodal and bimodal distributions, which at this point are a bit subjective to identify. If I ask you about these on an exam or something, I'll make it pretty clear. If it's something where the counts are very small and you see a little blip, that doesn't count as a bimodal distribution. But if you see large counts and clear modes, that's a bimodal distribution. I'll try not to put anything too in between there. Left and right skew are things that you now have several tools for identifying, both from numerical summaries and graphical summaries, as well as outliers. I won't read these out again, but here are the main things that you should take home and make sure you've learned from this lecture and from the lab. And with that, we're at 5 minutes to the hour. Are there any questions before we shut down? And then I'll give a 10-minute break so you have a chance to go and pick up a computer from downstairs, get a drink of water, whatever. Any questions? Is there anyone who needs a plugin who doesn't have one? If so, I'm going to go down and ask for power bars so that we could at least plug into the wall and provide power for a few extra people. Just put up your hand if you'd like me to get a power bar or two. I don't mind doing it. No, okay. What's that?
Thank you, Zoe.
Hmm?
Thank you, Robert.
Okay, good job.
For those that need to know, there's only the only office that I know of in this room that is accessible are right here. So do something.
Signing off. Thanks.
Move that.